Hi there! I decided to dedicate today's video to the design and realization of a useful lab instrument. There are several commercial versions available, but they are designed for professional use and cost a lot of money. For the casual experimenter with little money to spare, these devices are often out of reach, and that's why I decided to design and make one myself so we can have an affordable instrument at low cost. I'm talking about a device that can measure capacitance, or what I call a capacitance meter. The device I designed won't be able to take measurements of the parasitic inductance of a capacitor or its intrinsic resistance, and nor can generate a graph to show how the total impedance changes as a function of the frequency. However, even in its simplicity, it will be perfectly capable of measuring capacitance from single-digit picofarads up to 500 nanofarads. I know there are multimeters that are perfectly capable of measuring capacitance, but their range is not able to go so low. And here comes my instrument that, although it has a precision around 3%, it is still perfectly capable of making measurements good enough for a hobbyist. Let's then get into the details, but first, please take a moment to subscribe to the channel and consider also to become a patron. Links are posted in the description below. I posted there also a list of other links pointing to some pages on Amazon's website where I bought some of the materials I used for this project. Full disclosure, if you use one of these links to buy something, Amazon will pay me a commission, but that will not affect at all the price you'll pay. And now, let's begin. Before getting into the actual design, I will explain to you the concept behind the solution I used. As you probably already know, the capacitance of a device is expressed as the ratio of the charge accumulated on its plates divided by the voltage at the same plates. If you want to refresh these concepts, please take a look at my introduction on capacitors. The link is coming up right now on the upper right corner of the screen. The equations can be rewritten to find the charge. From there, with a simple trick, we get to the important point. Since this is an equality, we can multiply both sides of the equation for the same number, and the equality will not change. I will multiply the two parts of the equality by a frequency, which will be the frequency of a signal applied to the capacitor under test. On the left side of the equation, we now have the product of a frequency by a charge, which can be expressed in coulomb per second. This is exactly the value of the current that goes through the capacitor for the particular frequency f. And so, we can rewrite the equation as I equals FCV. See what happened? We have found that the current is proportional to the frequency. But, if we keep the frequency constant, the current will also change proportionally to the value of the capacitance. And this is what our meter will do. It will inject into the capacitor a voltage that varies with a specific frequency, and if we know the frequency and the voltage values, reading the value of the current will give us the value of the capacitance. I have found a microamp meter with a range of 50 microamps. To use that efficiently in this project, we just need to find a frequency such that when the capacitance is 50 picofarad, it will produce a current of 50 microamps. And this frequency can be calculated rearranging once more the last formula, which becomes F equals I over C times V. I'm going to use a power supply of 5 volts for this project, and I will tell you why later on, and I will need to change the alternate current going through the capacitor into a DC current so we can read it on the ammeter. To do that, I will need a couple of diodes which will produce a drop in voltage. And again, we will see these details once we look at the schematic. For now, I will just assume that the voltage of the capacitor, V, is going to be the voltage of the power supply minus the drop caused by the two diodes, which will be around 1.4 volts or so. And so, at the end, the voltage I will have to put in the previous formula will be about 3.6 volts. And of course, we already know that we want to have a maximum current of 5 microamps when measuring 50 picofarads. Substituting all these values in the formula for the frequency, we obtain that we will need a frequency of about 278 kHz. Note now that with this frequency we can read up to 50 picofarads. However, if we use a small frequency 10 times smaller, or 27.8 kHz, then, because of the same formula, we will be able to read up to 500 picofarads. And then we can read 5 nanofarads with 2.78 kHz, 50 nanofarad with 278 Hz, and 0.5 microfarad or 500 nanofarad with 27.8 Hz. We therefore need something that will generate these 5 frequencies for us, so we can use the right one depending on the range of capacitance we want to measure. Let's see how we can do that using a block diagram. We start, of course, with an oscillator that will provide the highest of the 5 frequencies. For the other frequencies, since they can all be obtained by dividing by 10 the previous higher one, we can just use a cascade of dividers by 10, easily available as a TTL ICs. Of course, if we use TTL ICs, we will need an oscillator that provides a square wave compatible with a TTL signal. And that is why I choose the 5V power supply, because the TTL circuits I decided to use require a 5V power supply. As for the oscillator, when we did the calculations, nobody made any assumption about the shape of the signal, so a square wave is just fine. The only thing that we need to make sure is that the duty cycle of this wave is about 0.5, otherwise the circuit might not work right, in the sense that we would introduce too many unwanted harmonics of the base frequency, and so we could affect the final measurement. Once the signals at these frequencies are all available, we will just have to use the one that gives us the range more suitable for measuring the capacitance we have. So we inject the signal in the capacitance, and we read the amount of current going through it. The amount of current will tell us the capacitance value. Here is the schematic of the device that we are building today. Let's start from this part here, which is the power supply. I'm gonna use a battery of 9 volts to do this, but I have also a 7805 voltage regulator, which will be used to fix the voltage of the whole apparatus to 5 volts. So even if the battery discharges a little bit and the value of the 9 volts changes and starts decreasing, we can still use the device safely and ensure that the frequency that will be generated by the 555 over here will not change over time. So we have this 9 volts battery. We have a push button which basically will be used when measuring the capacitor. This way the battery will only be used in a very short moment during the testing, and otherwise it will not be used. This will help making the battery last a long time. On the other side here I have also a resistor and an LED, which will tell us when the LED lights up that the device is operating correctly. Then this is the 555. You can see that it is connected in an unstable configuration. This is the two resistors that are used to regulate the frequency and the duty cycle. I used just a couple of trim pots, in particular multi-turn trim pots. This way I have a wide range to set up the correct values, and I can tune the device appropriately. C3 is the capacitor that regulates the frequency along with the two resistors, 2 and R3. C2 is a 10 nanofarad capacitor that is connected to the voltage reference so that it won't be affected by sudden changes in the voltage that can be caused by the switching of the counters that come later. And finally there is the 100 nanofarad capacitor on the BCC to further decouple the power supply on the 555. The output of the 555 goes, as you can see, directly here to the socket that we will be using for attaching the capacitors under test, and at the same time it goes to the input of the first IC, which is a 7490, which is a divider by 10. Each of these ICs is configured exactly the same way, and each one provides on its output, which is on pin 12, a signal which has the frequency of the input divided by 10. So when here we have 370 kHz and the output 12 here, we will have 37 kHz, 37.7 exactly, which will go to the other pin of the zero force insertion socket. and then this signal will also go to the input of the next divider, and the output again will go over here, ready to be used by a capacitor under test, and it will go back over here on the input of the next divider, and so forth and so forth. So basically at the end we have 5 different frequencies available to test the capacitors, to make measurements, and for the first one we will have a range of 50 picofarad with the highest frequency. Then for the first frequency divided by 10 we will have a range of 500 picofarad, and so forth, 5 nanofarad, 50 nanofarad and 500 nanofarad. The capacitor under test will be put on the zero force insertion on the 2 opposite pinholes. For example, 9 and 8 will be to test capacitor up to 50 picofarad, pinholes 10 and 7 for the range of 500 picofarad, and so forth, as you can see from this little table. Once the capacitor is inserted in this circuit, it will let the signal going through it end in this position here, where there are these 2 diodes, D1 and D2, which basically do the job of providing the appropriate current to the micrometer, which is connected over here. When there is a positive crest over here, the capacitor is charged from the signal over here through the sockets and down to this diode D2. And then when we are on the negative crest of the signal, then we will have a negative on the side of the capacitor, and thus this will polarize correctly this diode, which will be on, and so basically the current will flow from here and through the capacitor, which this way will discharge. Let's see now how I tested this schematic to make sure it works before building the final version. This is the circuit I mounted on my breadboard to test the capabilities of the circuit I designed and to verify that everything works as I expected. So let's take a look closer. So this is the 555 that acts as an oscillator. Here's the capacitor for the timing constant, along with these 2 multi-timer inputs. This one on the left is the one on the top of the schematic that basically allows us to adjust the duty cycle of the signal, of the square wave, and this one adjusts the frequency. Of course, when we move the one for the duty cycle, the frequency also changes a little bit, but moving from one to the other a little bit at a time, and we'll soon see how, helps us to adjust both the frequency and the duty cycle the way we need it. Then the output of the 555 is sent to this chain of 7490 ICs, which basically are, like we said, dividers by 10. So the frequency in input here comes out divided by 10, and then divided by 100, by 1000, and finally by 10,000. Originally I was thinking to use a rotary switch to select the frequency that I needed to go through the capacitor, depending on the scale range that I wanted on my instrument. But then, since I was using anyway this ZIF socket, zero insertion force, I thought, why do I need a rotary switch? I can just take the various outputs here and put them on different lines on these sockets. So this one will be the one with a higher frequency, this one with the next one 10 times lower and lower and lower, and so all the frequencies are available over here. So basically, rather than using a rotary switch to select the frequency, I choose the position on this socket where to put the capacitor to decide which range of measurements I need. And you can see, besides that, a few more things to notice now are, for example, the capacitors that are supposed to do some filtering of the signal on the power supply. So we have this one on the 555, and then you see all the others here on the 7491. Here there are the 2 diodes that are supposed to basically play on the capacitor to act as a pump charge. And so basically this is the output where we are going to measure the current to the capacitor, and this is the ground connection. So basically we are measuring the current between these 2 points. And just because I needed it for adjusting the value of the frequency and the duty cycle, here is the output of the 555 available to connect it to an oscilloscope. And that's it. Let's see now how this works. So the first thing I'm gonna do is to connect the power supply to the circuit, and of course here I have already my power supply generator over there, which is already set for 5 volts. Right now I'm gonna use that one, and I'm not gonna create the power supply specifically for this one, since I'm gonna just use a battery in a 7805. This is a very stable circuit, I don't need to test it. So for now I'm gonna use this. The cable is already connected over there, so I just need to plug them in. So the circuit now is powered up. And now I'm gonna connect the probe of the oscilloscope, which is gonna be on ground here, and on the output of the 555 for now, which is here. So when it's time to do the tuning of this oscillator, you basically start playing first with the 2 trim pots on the center position. These trim pots are about 10 turns, so I basically put them at 5 turns at the very center, and then I started dealing with that. First trying to adjust the duty cycle, then the frequency, and then back and forth until I had the frequency that I needed, which was about 390 kHz. And here you can see the effect of what I did. You can see that the square wave that I was supposed to have very clean, it really is not clean. There is this thing over here that is not exactly right, but I assume this comes from the parasitic capacitances of the breadboard, which is not made really for frequencies that high. So the hope is that when I build the circuit in its final configuration, I will not have this kind of gap over here. But anyway, even if there is, it's not a big deal, because what we really need is the way to charge and discharge the capacitor continuously, and this works anyway. So let me show you now the effect that this trim pot does on the wave. So let me put this here and let me show you how this changes by changing the position of the cursor. Now we're moving in one direction. You see how it's getting closer, and the duty cycle changes. So basically, in this case, this part is getting smaller, this part is getting larger. And if I go in the opposite direction with the trim pot, it moves the other way around, as you can see. There we go. I'm gonna leave it in the position that I think is the right one. There we go. There. And now, let's look at the frequency here. This is 298 kHz. So I'm now gonna start moving the other trim pot now, the one that actually adjusts this frequency. And look what happened when I move it. See? The frequency increases, and in this other direction instead decreases. So once the duty cycle is set correctly, this is about right, and I can increase and decrease the frequency without having any more changes on the duty cycle. Now, how do I definitely set this? How do I tune it for the best functionality? Well, first of all, let's attach to the system now the micrometer that I need to take the measurements. I got this instrument. This is quite a good instrument. It's a small one, but it's quite good. You can see as a class 2.5. It can stay either horizontal or vertical. Has a mirror behind, so we can take the measurements, trying to cancel the effect of the parallax. And let's connect now this instrument to the circuit. This is the positive side, and this is the negative. And now the negative is going to go to the output. Remember when I explained to you the circuit, how it worked? Basically the voltage of the capacitor will be reversed than the power supply. So this goes here, and the other one, the positive one, goes to ground instead. So let me put it over there. There we go. And right now, of course, there is nothing because there is no capacitor inserted in the SiC socket. So let's put now a capacitor. I have these 4 here, which I basically measured some other way, and these are very close to their actual value. I had to go through many of them to find out the right ones. You may want to buy just one single capacitor of one of those that are used to tune up this kind of devices, which is very precise. It costs a little bit more, but you will buy it just once. Anyway, this one is 50 picofarad, so I'm gonna put it in the top slot because that's the one that has the maximum range of 50 picofarad. So I'm gonna put it here, I'm gonna lock it here. And you see the index here is already mostly in the right place. Let me adjust on the twin plotter for the frequency until we measure exactly 50 over here. Okay, here I'm going in the opposite direction, so I turn around, and here we go, this is 50. Now let's remove this one and let's try again now with another one. Let's try with this other one. We should be able to measure this correctly. This is 33 picofarad. So I'm going to put it over here and look at that. It's just perfect. And then let's try another one. This is 9 picofarads. So I'm going to put it over here. Again, same place. There we go. And look, 9 picofarads. So you see it's very linear and I can measure just about anything I want. This guy is 6 picofarad. So let's try this one. Let's see if we can still have a good measurement. So still the upper slot. And here we go, 6 picofarad. Now let me show you what happens if I use a different kind of range. For example, this was a 50 picofarad range. Let me go in the 500 picofarad range, but it's still using this 50 picofarad capacitor. Let me show you what happens in this case. There we go. And see, I'm measuring about 50 picofarads over there. Actually, this thing measures a little more than that, but you have to understand that this kind of analog instruments work better on the right side of the scale. On the left side, they are less precise. And anyway, this is a 2.5 class instrument, so this kind of reading with this capacitor of 50 picofarad is perfectly within the compatibility of this device, so everything is fine. Let me see if I can find another kind of capacitor, a bigger one, so you can see how the other one works. This one is a 220 picofarads, so this goes at the second slot over here. Let's see how much we can measure with that. Look, it's 220, just a little touch more. Of course, if you have more than one reference capacitor for the different kind of ranges, you can repeat the adjustment of this potentiometer for the different ranges and choose the one final arrangement that gives you the best reading in all the scales. So next step now is to take away the components from here and actually use them to build the final circuit. Here is the box that I designed for this device. It's very simple. There is a base which will contain all the circuitry and the battery in this location, and then a front panel that will be attached on the top of the case. The front panel has a number of holes, one for the micrometer, one for the ZIF socket, one for the LED, and the last one for the push button. Very simple to create. Here is the code to do it, and I will publish the file for this code along with the schematic in my eleneasy.com website, of which I'm putting a link down below in the description of the video. Here is the box for a new device. It just came out from the 3D printer. So this is the part that contains all the materials, and this is the front panel. On this slot we will put our battery, and this one will accommodate instead the micrometer, and from this fuse we will have this kind of thing that comes out from here. Basically we will put all these three elements, the push button, the diode and the ZIF socket, on this little board, which will be attached right behind this panel, and so we will be able to control all the functionalities of the capacitance meter, and we will be able to work with that. And this will go on top over here. The rest of the circuit instead will go down on the bottom over here, and this circuit and the one that goes on the bottom will be connected to some cables. So that's how this is supposed to work. Okay, this is the circuit completed. This part is the one that goes behind the front panel, like this. And this is the one that goes on the bottom with the rest of the circuit. I haven't mounted yet the ICs over here because first I want to test the power supply, and then I will test the pieces one by one, inserting them one, testing, and so forth. So let's see if the power supply works. Since we have digital ICs that work at 5 volts, I had to put this 5 volts regulator because a 9 volts battery is not good. So let me connect to the battery now. There we go. And of course at this point nothing should happen because the push button is not pressed. If I push it we should see the LED coming on. And yes, that's it. So now let's see if the power supply comes in the right places one by one. For the 555 it should be between pin 1 and pin 8. So this is pin 1, this is pin 8, Let me first turn this on. Okay, so 1 and 8, there we go. Let's measure now. And here there's 5 volts. Good. And then for this one here, all the others should be between the pin 5, it's the positive, and the ground is pin 10. 5 and 10. So 1, 2, 3, 4, 5, 8, 9, 10. These two are the pins. Push the button. And here is the 5 volts. Let's go to the next one. There we go. And yep, 5 volts. And then here 5 and 10. Yes. And the last one. Yes. Okay, so everything is fine from this perspective. Now I'm gonna try insert the 555 and see what happens if it oscillates, and eventually we'll tune these two trimmers to get the right frequency and the right duty cycle. Okay, I inserted the 555, making sure that I didn't make any mistake. Now let's turn on the oscilloscope and let's use that to do the rest of the operations. And adjust the light so we don't be bothered on the oscilloscope with that. So I'm going to use this channel here, and now on the circuit over here we are gonna have to connect negative and the output over here. This is ground. I'm gonna grab it right there. And then pin 1 here should be able to see the signal. Okay, so now let's go back to the oscilloscope and let's see what happened when I push the button. And there we go. Here's the square wave. Seems like the duty cycle is already set, probably because I already did it in the prototype and I'm using the same trim pots. And the frequency, 286 kHz, could be the right one too. We will have to check that later once we finish setting up the circuit. Anyway, so this works. So now let's put the next IC and let's see how it works. Let me grab it. I'm gonna put it right over here. There you go. At the output of this one, which is pin 12, or pin 1 of the next, I should see now a frequency which is 10 times smaller than the previous one. So let's go back on the oscilloscope and let's push the button. Okay, 28 kHz. Let me adjust this a little bit. And there it is. Let me put some more cycles over here. There we go. Okay, so let's put now the other IC, the next one, the next divider by 10, right here. You need to be careful with the pins, not to bend them in the wrong way. It should work just fine. Okay, let's try this other one now. The output is right over here, oscilloscope, there we go. And yes, now is 2.8 kHz. Let me move this a little bit again. Okay, and now let's put on the next IC. Be always careful to put the pin 1 on the right side, otherwise you may break the IC and make it not work anymore. So let's check it out again here, oscilloscope, and here it is. Okay, now it's 285 Hertz. There we go. And now the last one. There we go. Good. And so this time we have to go on pin 12 to see the output. Over here. Let's go back there. And we push the button. Yes, now it's 28 Hertz. Good. So everything seems to work fine on this board, at least. We still have to check this other one. We need to make sure we can take the measurements the same way we did before. Here is my reference capacitor of 50 picofarads. This is the slot that has 50 picofarads scale, and I'm gonna need now to connect the microamp meter. Okay, I'm gonna use this for now. and then at the end we will put everything together. So this goes to the negative, this goes to the positive. There we go. So let's give it a try now. Let me see if I can show you everything that happened. So I push the button. Yep, there we are. Perfect. So I don't think I need to do anything else right now. Now we have to do the final assembly and we're done. So we need to do two things now. We have to put this in place over here and lock it in place. And then we have to put this other one on the back. And finally we have to attach also the micrometer. So one by one, let's do all these things. First, for this one, I'm going to put something on the bottom to stick it in place. Let me use the usual sticky pads. Okay, I got this one. Yeah, should be enough to hold in place this element. So let me clean this up. Let me stick it in place. I'm trying to push it as much as I can so it will be thinner enough not to create issues when I close the lid of the system. So now this is gonna go here like this, and this won't move anymore now. The battery will be located over there. I can put it on right now. It's not gonna work until the push button is connected. So this is done. Now here, let's first attach this in place. I need some hardware to do that. Okay. First of all, we have to anchor the ammeter to the front panel. Now I have to tighten it up so it won't move anymore. Need to be careful not to tighten it too much because otherwise I can break the instrument. Okay. So this is in place, solidly in place. Now I'm gonna have to put these two little tabs. They're gonna go over here and will be held in place by this little screw. It's probably better if I solder these guys to these cables. So let's do that in just a moment and then we finish. Let's get the first one. We later cut the excess cable. Now we cut the excess. Same for the other one. Okay, that's done. Let's cut the excess here. And now we can connect these pieces over here. First, let's attach this in place. And for this one I think I'm gonna need some glue because this has to be very close and I really don't have any other way to do that. So what I'm gonna do, I'm gonna hold them in place with little pieces of tape and then I'm gonna use some glue to hold them in place. Once the glue is dry and cured, then I will move on and I will continue the assembly. But until then I need to wait a little bit. I'm gonna put some glue over here, over here, over here, and over here. Let's do that. And then I will have to wait. Unfortunately, this means I will have to wait until tomorrow to finish. I'm done with that. And now we just have to wait. Okay, here we are after the glue has dried out. I think we can now remove this tape and everything should be fine. Let's check it out. And here it is. As you can see, the device is not moving anymore, so everything should be okay. There we go. Yes, the device is firmly in place. We can also connect now the cover to the button. There we go. Very nice. Now we're going to connect the power instrument to the system using these cables that come over here. So for those I'm going to use the screws that come with the instrument. So this is all set. Now what is left to do is to connect all the cables between this and this and then close the container. So the device is all assembled. Now I should be able to close it.
There we go. Okay, and the device is ready. Let's test it now. Let me use again the 50 picofarad capacity as a reference. And yep, it goes a little farther, so I have to do some little adjustment on the 20 kilo ohm input, which is this one over here. So I'm gonna turn on this now and adjust the screw here. There, that should be okay. So now we can close the device, and there it is, ready to work. Let's give it a try with some other capacitors just to see how it behaves. So I'm gonna take a few of those right here, and let's see what we can do. So this one, for example, is 220 picofarads. So this goes in this other slot, which is the 500 picofarad range. And yes, 220, very cool. Let's try something different now. If you don't know how much is a capacity in particular, always start from the higher range and then slowly go down. For example, let me take this one. So let's start from the top here and let's go down a little bit at a time to see if we can make a more precise read. Okay, so this tells us that we can go higher because we are below 10. Let's put it over here and let's see if it still works. There we go. See, this is too much already. So this was the correct reading. And what we can see is a little less of 100 nanofarad. Let's try with exactly 100 nanofarad. Let's see what happens with this one. Yep, 100. Let's try with something bigger. This one is supposed to be 470 nanofarad. Let's see what we can read on this. And there it is. It's about right. Perfect. So the device works. And now what is left to do is to just add some labels over here to basically identify the various slots. 50 picofarad, 500, 5 nanofarad, 50 nanofarad and 500 nanofarads. So I won't make mistakes in the future when I try to use this instrument. And you won't either. I have prepared this one with my printer and I will stick it right here in position so we will know exactly where are the slots for each range of capacitances. And the instruments is completed.
And there you have it. The capacitance meter is now complete and ready to be used in lab. This is fundamentally an easy project to go through. The one thing that is important for you to have is a sample capacitor of which you know the exact value. Or at least a capacitor with a very small tolerance, smaller than the tolerance of the analog ammeter used to take the measurements, so that it won't account much for measurement errors. In my case, I used an instrument with a precision of 2.5%. The capacitor I used for tuning was not of high precision, but I was able to have it measured with a professional capacitance meter, and so I was able to do a reasonably good tuning. Before closing, I would just like to invite you to give me a thumb up and to subscribe to the channel if you are not subscribed yet. Thank you for watching this video till the end, and I'll see you in the next video. As usual, happy experiments!